in today's assignment, you're going to be watching a screencast. This is the screencast, duh. But hopefully you've also gone into this and opened your own version of this document. And as you are watching the screencast, you should follow along and put your answers in here as you go. Okay, so as you're starting and stopping the screencast, type in here. So probably you're going to want to do sort of make this a little bit smaller, for example, and then have a video going on the side, right? So you can watch the video and do this. Or if you prefer, you can, multiple people can watch the screencast on one screen, okay? So I want you to type your answers into here. Do a really thorough job because this is going to be a really great study guide for you. When you're finished, if you want a hard copy for yourself, you can print it. You don't need to do anything for me because I can automatically see this. So this is going to allow me to check and see that your answers are on point, that they're thorough. It'll help me see what questions maybe you're not so clear about or what concepts you don't fully understand. But you need to do a good job. Be thorough here. The slides follow along in order of this particular document. When you're finished, don't forget to hit submit my document. Okay? If you struggle with that, get other people in class to help you. We've done it before. Lots of people know how to do it. But if you aren't quite sure, just ask somebody in class. Okay? All right, so start and stop the video as needed in order to answer questions. Okay, I'll give you some examples. Okay, so we've been talking about energy types, energy transfers, efficiency, and so on. More in the physics sense than in the chemistry sense, but now we're moving into more of the chemistry part of this unit. So for today, you should be able to, by the end of today, identify reactions as being endothermic or exothermic, so we're going to talk about those terms. And you need to be able to construct pretty simple energy diagrams to represent energy changes in chemical reactions. So we'll go over those things. In addition, what's not on here is you definitely need to understand what is happening in a chemical reaction, what is a chemical reaction, what happens to the energy in a chemical reaction, and then what are some, how do you know if a chemical reaction is happening or not? So we're going to talk about those things too. Okay, so the first thing you need to do is just amongst yourselves, talk about what do you understand, or if you want to do this on your own, what is heat, what is thermal energy, and what is temperature? They're all different. So they're very similar, but they're not the same, and it's important that you understand the differences. Take a minute as well to kind of draw a little cartoon to explain what's happening to the water particles as a hot plate warms up a beaker of water. Okay, so what's going on there? Is it what's happening to the water molecules themselves as you heat up water? And then finally, how do you think it's possible that chemical reactions can produce energy? How can they produce? Now, can we really produce energy, or can we just release it? Okay, so think about those things. Take a minute, stop the video, either do this on your own or talk amongst your table group. And when you're ready, go ahead and click on play again. Okay, so what is thermal energy? Thermal energy is the actual energy. Okay, it's the amount of joules. It's the kinetic energy of the particles in a system. So the kinetic energy of the molecules that are moving in your bottle of water, for example. That is thermal energy. Okay, we can measure that thermal energy by we can measure the average kinetic energy of those particles, and that's what temperature is. So temperature is in degrees Celsius usually, or Kelvin, or sometimes Fahrenheit. Thermal energy is a measurement of energy, so its unit is the joule. Okay, so then we come to this sticky one, heat. Heat is a tricky one because heat, the way we use heat in terms of our daily lives isn't the physics, chemistry type term for heat. So heat is the movement, the flow of thermal energy. So it isn't thermal energy itself, it's the movement of that thermal energy from an object of higher temperature to an object of lower temperature. So for example, if you are standing outside barefoot in the snow, you have higher temperature than the snow does, and so thermal energy is going to flow from your feet into the snow, causing the snow to start to melt, right? So that is that flow, that action of movement is what we call heat. And you're going to learn how to calculate that from data. So one of the ways that we measured energy changes in a chemical reaction is by measuring the change in temperature before and after a reaction. Okay, and that's heat. That flow is heat. Okay, so what the heck is a chemical reaction? All it is the rearrangement of atoms in one or more of the things you're starting with, which we call the reactants, to form new substances, which we call products. So remember, atoms are just, you can think of them as like little balls. So they're the same, they're made up of elements, so like carbon or hydrogen, and those atoms in a molecule are bonded together. So they're held together by chemical bonds. Those chemical bonds have what kind of energy do you think? Yeah, chemical potential energy. So in a chemical reaction, these are some terms you need to know. Reactants, these are the chemicals that are reacting. Sometimes it's only one thing. You may have a chemical that's just breaking down into two. But in any event, these are the things that are going to react. They're always on the left side of the arrow in a chemical equation. The products are the things that are formed, so the chemicals that are formed. So you've taken a bunch of atoms, you've rearranged them and bonded them together differently, then you get products. These are always on the right side of the arrow. So here's an example. This is just a word equation. I didn't do the chemical equation, but it's the same idea. So you have ethanol plus oxygen. These are my reactants. And then we say yields when we have an arrow. Yields, water and carbon dioxide. These are my products. What else is it going to yield? A lot of energy. So we're going to watch this little video. So this is a fun little demo. If I were there, we would try to do it. So she's taking ethanol, which is an alcohol. It's very volatile, meaning it will form a gas. It'll go from liquid to gas with just a bit of shaking. So she's going to shake the bottle up a bunch. I'm going to fast forward this a bit. Shaking, shaking, shaking. Shaking, shaking, shaking. Shaking some more. Okay. And then basically she's not got any liquid left in the bottle. It's all become a gas. Okay, so there's this gas that's inside this bottle. So see, no liquid. Now she's going to light a splint. And dun, dun, dun. And then she lit the gas on fire. So that is what we call a combustion reaction. And then you'll see what the product is. It makes a really loud noise. Okay, so in this one, you can actually see the chemical equation as well. So here's ethanol, C2H5OH, plus oxygen, gives us carbon dioxide and water. What's not in here is energy. There should be energy over here because there was a bunch of energy released, right? You could tell that just by the fire that came out. We'll talk about these numbers later, like why is it 3 and 2 and 3 and so on. Okay. Oops, wait a minute. So then what you're going to see is, remember there was no liquid in the bottle before she lit the match, before she lit it on fire. And now look what she gets. Cool, huh? That's one of the products, water. Okay. So let's talk about how we know when a chemical change or a chemical reaction has occurred. Now we just saw one example, right? You had sound, a big whooshing sound, you had production of light, and you had the production of, or you had heat, so thermal energy moving. But let's go through this in a little more detail. So on, oopsie, question 5, there's a place for you to write these things down. So I'm sure a lot of you guys have put baking soda into vinegar before, and what do you get? Bubbles. So evolution of a gas or formation of a gas is one type of evidence for chemical reaction or chemical change. Now, not in the case where you're like boiling water and you get bubbles from that. Okay, another one, heat and light. It's another example. So production of heat or thermal energy and light. That one also had sound. Here is the formation of a precipitate. So this is where we took two clear liquids. They both had stuff dissolved in them. When you mix them, you get a solid. So that's what we call a precipitate. And we also got a color change here. Don't worry, I'm going to summarize all these at the end in another slide. So that is formation of a precipitate. This is in slow motion. It actually changes really quite quickly. And then here, okay, the guy's squirting a little bit of water onto a wooden block. He's got two different solids, two chemicals right here, and they're both solids. And he's going to put one into the other, or she, can't tell. Stir it up to mix them together. And if you touched that beaker, it would feel really cold right now. You just put the beaker on the moistened block, and it's going to freeze the block because the temperature went down so much. It got very cold. And then this one's kind of my favorite. They are adding a liquid to some iron filings. It's basically vinegar and iron filings, and now they're smelling it, and it really stinks. So it goes from smelling like vinegar to smelling like stinky farts. So sometimes producing an odor will have the same effect. Okay, so let's summarize these things in case you missed any. So formation of a gas, change in odor, change in color, formation of a solid, which is what we call a precipitate, release of sound sometimes, and change in temperature. Now you have to be careful here because, again, sometimes you'll just be heating something up and you get bubbles. That's not really evolution of a new gas. And a change in temperature is not always an indicator, because if you're just heating water, for example, or heating anything, you're just getting it hotter. It's still the same thing. Okay, so you have to be a little bit careful with those ones. We're going to focus on change in temperature because this is really going to be something we can measure to see what the energy changes are that are going on in chemical reactions. Okay, so in order to think about this, we also need to go back to that law of conservation of energy, which states, as you know, energy cannot be created nor destroyed, only transformed or transferred. So what that means in terms of chemistry is the total chemical energy that's stored in the chemical bonds of the reactants, the things you start with. All of that energy has to be accounted for after the reaction. It's either going to be stored in the chemical bonds of the products, or you have to, if it's not all stored in there, then that means some of it was released to the surroundings as thermal energy, or if there's more energy in your products, more chemical energy in your products, that means that it had to absorb that energy from the surroundings. So you have to take account of all of it. And that's partly how we figure out, both experimentally and mathematically, what are the energy changes going on in a reaction. Okay, so how can we tell? A lot of times the main thing we do is we tell, does the surroundings get colder or hotter? So an exothermic reaction, think exo means out, exothermic, out, thermic energy, thermal energy. So it means that your reaction is releasing thermal energy to the outside. So this is an example, would be one of those instant hot packs you maybe use for skiing on a cold day. So when you shake it up, the chemicals mix together and they make products. The products have a lower chemical potential energy than they started with. So where does that extra energy go? It goes out to the surroundings. So it goes to your hands. It feels warm. An endothermic reaction is the opposite. You start with reactants that have lower chemical energy than your products. So like in a cold pack, you hit the cold pack, you mix the chemicals together in doing that, and they suck energy out of the surroundings to make the products. So your chemical energy is higher in your products, which means the surroundings got colder because that thermal energy went into your products. Okay, here's another way of looking at it. So endothermic, heat gets sucked out of the surroundings into the system. The system just means the actual molecules that we're talking about. And Q is heat. So heat is, or the Q value you'll learn to calculate later is greater than 0. Don't worry about those right now. Basically, energy gets sucked out of the surroundings and goes into the system. So the temperature of the surroundings is going to go down. That's why the ice pack feels cold. The chemicals themselves have more energy, but that energy was being sucked out of what you're touching, which is part of the ice pack. Exothermic is the opposite. So the temperature is going to get warmer, the surroundings will get warmer because energy is leaving. You have extra energy that's leaving from the chemical reaction. So this is another way of looking at it, and you do need to be able to draw these. So if we're talking about, let's call this chemical potential energy, and this is the reaction over time. It's not really over time, it's more of a non-numerical type representation. But if this is the total chemical potential energy of my reactants in my chemical bonds, and this is the total chemical potential energy in my products, that means I had all of this energy that had to go somewhere. And where did it go? It went out to the surroundings as thermal energy. I can measure that by measuring how much the surroundings temperature changed. The temperature is going to go up here, right? Because energy is released to the surroundings. So the temperature is going to get higher in my surroundings. So I can actually measure that temperature change and then through some math figure out how many joules of energy were released. This is the opposite. This is an endothermic reaction. The chemical potential energy of my reactants is low in comparison to my products. So where did that energy come to give me higher potential energy in my products? It got sucked out of the surroundings as thermal energy, so my temperature would go down here. And I can figure out how much this energy is by measuring that temperature change of my surroundings. It's pretty cool. Okay, you should be able to answer these questions. What kind of energy is in the reactants? Did you say chemical potential energy? Good. How about the products? Same thing, chemical potential energy. What kind of energy is transferred? Give you a hint. Right here, right here. Thermal energy. How is it transferred? As heat. Okay, moving on. Okay, here's just another example. Total energy of the reaction is conserved. Okay, so if we're saying, wait, but we didn't conserve it because the products is lower, well, that means we account for this. So really this energy release would go over here. We would say plus 375,000 joules or something like that, whatever it is. Okay, so we still have to account for it because this energy that dropped, that drop in energy from reactants to products goes to somewhere. We have to say how much energy that is and where it went. Okay. So in this reaction, where is the energy that is released coming from? It's coming from the chemical potential energy in the reactants. And what is the energy that is taken being in here? What is it being used to do? It's being used to really store more energy in the products. So it's in the chemical bonds. We're going to draw more sophisticated diagrams of these, but this is just kind of the big picture. Total energy in the reactants versus products. This is the energy change right here. And that is what we're going to find out how to do in the lab. All right, so if you look at this one, would you call this endothermic or exothermic? Reactants have more energy than the products. Energy in our chemical bonds goes down. Where does that energy go? So what would it be? How about this one, endo or exo? Reactants lower than the products. All this energy, extra energy came in from the surroundings. So is this endo or exo? Oh, I didn't give you the answers. This is exothermic, right? Because that energy is released. It's going out, exo. Here you've got energy going in, endo. Overall, now we're looking at before and after the reaction. We're not looking at what's happening in between. Okay, this is just what we start with, what we finish with. There's other stuff that's happening in between here that we're going to talk about later. But big idea, start to finish, energy goes down. So it's released to the surroundings. Okay, now what you guys need to do, make sure you've answered all the questions thoroughly. And then go to your booklets. There is a lab on pages 19 and 20. And I want you to read through that lab. We're going to do it on Monday. You're not going to do a lab report. You are going to collect some data and observations. It's really just to give you some experience with endothermic and exothermic reactions and what those look like in the lab. How do you know? Each group will probably do just 2 of the 6 reactions. We're going to split up just because of timing. So it's really important that you are very well prepared to come in and do this. All right, have a great weekend. If you do finish early, by the way, I would suggest you go back through these terms and practice them. I will try to post a little Quizlet also, or a Kahoot on Schoology in case you want to just go through that and quiz yourself. All right, have a great weekend. Bye.